You have the definition of a wave here, so you can go over that, you can read it. And this is just another form of energy. So we talked about rotational energy, we talked about all the other kinds of mechanical energy, but this is a wave is just another way of carrying energy from one place to another. Now here we carry the energy, but the matter doesn't move. So for instance, if you take a slinky, okay, and you create a pulse in the slinky, in other words, you move it side to side. So what happens if you follow one part of the slinky here, you're going to see that there is a pulse that travels down the slinky, but this particle here never travels with the wave, with that energy. So this particle just goes up and down and it goes back to its equilibrium position. But there is some energy that got transmitted to the other end. Now, we're going to talk about two kinds of waves. Okay, there is, you have your mechanical waves, which require a medium to travel. So for instance, without a slinky, you can't have a wave going down the slinky. Sound is also another wave that's mechanical, okay? Because without sound, and I'll show you this in class, I'll show you a video, without air, sound cannot travel from one place to another. So the air particles have to be present. So we'll do a demonstration in class. There are waves that do not require a medium to travel, okay? So an example of those is the electromagnetic waves. So it's basically anything in the electromagnetic spectrum. So you can just take light. So if there is no air or if there is no matter in this room, the light will still come on. Okay, so those are the two types of waves. Now this is just some definitions that we're going to be using, some terms we're going to be using for waves. So the amplitude, and you probably learned a lot of this stuff in your math class, in your trig class. The amplitude is basically just the distance from your equilibrium position. So this is your equilibrium, okay, and the highest point or the lowest point. So that's why you take the absolute value. The wavelength is the length of the wave. So basically, it's the length of a cycle. So when you start to repeat yourself, you pretty much the distance covered is a wavelength. Okay, it can go from these 2 points here. You can go between this point and this point. It can go between this one and this one here. So all those distances are wavelengths. The period, which I think, yeah, period here, this is uppercase T, is the time it takes to travel a wavelength, right? In other words, it's the time it takes to make a cycle, to go back to the same position you were in before. Okay, a cycle is just, you probably can figure that out. Okay, a frequency is how many cycles you do per second. Okay, the period is the time for one cycle. So you can see those two ideas are reciprocal of each other. So I think we can say that T is the reciprocal of F, and F is also the reciprocal of T. Okay, now you have your crest is the highest point here, your trough is the lowest point. Okay, these are just definitions. The amplitude I talked about before. The frequency is how many cycles you do per unit time, per second. And the units for frequency is hertz, okay, or cycles per second. Okay, the period is just in seconds, and it's basically how long it takes to do one cycle. So this is all stuff you can read on your own and figure out. You did a lot of this in math. Now let's look at formula for wave speed. Okay. Now, speed is distance over time. Okay. But in the case of the wave here, we can just say that it's the distance traveled by the wave is basically the wavelength over the time it takes to cover a cycle, which is the period. Now we know that the relationship between T and F is inverse. So we can just say that 1 over T is frequency. So this is going to be lambda times frequency. And we'll come up with another formula for speed of the wave on a string. Okay. Now the problems we'll do in another video. The other thing I want to talk about is something called phase shift. So if I take 2 points here, A and B, okay, we say that these 2 points are in phase. In other words, their positions are identical as the wave is traveling. If we take A and C down here, okay, we say that A and C are 180 degrees out of phase. And if you think about it, there is half a period difference between these two positions to go from this place to this place. So that's half a period, and this is a full period. So when the difference in time is a multiple of 4 periods, we say that the two points are in phase. Okay? When the time between the 2 points is a multiple of half a period, we say that they are 180 out of phase. Well, what happens when they are a quarter of the period? So like between A and D, or between D and C. So that's a quarter of a period. We say that they are 90 degrees out of phase. So when one is maximum or minimum and the other one is 0, they are 90 degrees out of phase, or pi over 2. All right, so I'm just going to jump right to the different types of waves. Okay, this part should be pretty straightforward, everything that we're going to do in this video. Okay, you have your transverse waves, you have your longitudinal waves. So with the transverse wave, the medium, the wave travels in one direction, but the medium vibrates perpendicular to the direction of travel of that energy. Okay, so in this case here, a transverse wave would be like taking a slinky and creating a pulse to the side. Okay, so the material, the slinky travels sideways, okay, but the wave travels perpendicular to that direction of travel of the slinky. And longitudinal is like if you bunch up a bunch of coils and just release them. Okay, so the medium travels forward and back, and the wave or the energy travels forward. So they are parallel to each other. So the direction of the travel of the energy and the material are parallel. In transverse, they are perpendicular. Electromagnetic waves, maybe we can touch on that when we do light after the AP exams. Okay. Now what we're showing here is just the analogy between a transverse wave and a longitudinal wave, right? And you have all your definitions right here. So this is a compression, which is kind of like the equivalent of a crest, and this is a rarefaction, which is the equivalent of a trough, basically. All right, let's look at the behavior of waves, and I have a simulation that I can show you here. So with this simulation here, I'm going to send a pulse, okay, starting from here. This is a generator, so this generates a pulse, and it's going to come to this end, and there are two cases here. This end can be fixed. In other words, this rope can be tied to this end, or it can have a ring there, which means it's free to move up and down. So let's see what it looks like. So I'm going to start with I'm going to make it fixed at the end, okay, and I'm going to reset this and send a pulse. Okay, we're just going to do a pulse. Okay, so let's see what happens when it gets to that end. Okay, and I'm going to do dampen to 0. In other words, it's kind of like damping is like friction for waves. Okay, and if you notice, when it reaches here, when it's going up from the top, when it reflects from the bottom. So if it's a fixed end, it reflects coming back down the other way. And this is going to be very important when we do interference. Now I'm going to stop this, and I'm going to do a loose end, meaning like this part of the rope can move up and down. It's not tight. So let's see what it looks like. So it looks like it comes back the same way. Okay, look. So it comes back the same way on that side, but since this is fixed, it always comes back the opposite way, right? Okay. So let's go back to our document. Okay. Okay. What do we call the reflection of a sound wave? I think you can answer that. We'll talk about it in class. Okay. Okay. How a wave reflects depends on the kind of boundary, meaning like if it's fixed or if it's soft or loose end. So if it's fixed, it comes back inverted or flipped. And if it's loose, it comes back the same way. Okay, so if it was up, it comes, when it reaches the end, it comes back the same way. So here are some examples here. So if you have a less dense medium going into a more dense medium, and we're going to do a lab on this, so we're going to have a slinky on this side. We're going to have what do we call a snaky, which is basically a slinky with the coils that are very, very tight. Okay, and we're going to send a pulse from here. And what we see is we're going to treat this something that's more dense as a fixed end, in other words, right? So when this pulse hits here, it flips. Okay? But there's always something that gets transmitted to the other side. So basically, if you take the amplitude of these two together, because of conservation of energy, if you take these two and add them together, you should end up with what you started with. Okay? Now let's see if we go from more dense. So I'm going to make something thick like that. That's more dense. That's going to go into less dense. Now let's see what happens. Now you're always going to have a transmission. Something is going to pass to the other side, and something is going to reflect. So if you send a pulse like this, okay, when it comes back, it's going to come back the same way, but except that it's smaller because some of the energy got transmitted to the other medium, which is the slinky in this case, and you're going to do a lab on this. And here on this side, you're going to see something that gets transmitted. So the transmission does not change direction, but the reflection can change direction depending on whether it's a loose end or a fixed end. Okay. Refraction is the bending of a wave as it passes from one medium to another. An example would be like if you're looking at a straw inside a glass of water, you're going to see that the straw is kind of bent, and the reason for that is the speed of light in water is different than the speed of light in air, so that's why it looks like it's bent. Okay. Now, if you have a string and there's some tension, there's a formula for the speed of the wave in that string. And this is only true for a string or a rope or something that you can put tension on. So this V, and we'll do a lab on this, or maybe we'll do a collective lab, a group lab. V is Ft, which is basically the tension in the string, divided by what we call the linear density, right? So the linear density is basically just like you do with the volume density, which is mass over volume. The linear density is just mass over the length of the string. So if you take a piece of the string and you want to find its linear density, you put it on the scale, you weigh it. So let's say this is 2 grams. You measure the length of it. Let's say it's 50 centimeters. You can find its linear density by doing 2 over 50 after you change them. You change the 2 to kilograms and the 50 to meters. That's pretty much it. Okay? But we're going to do that in a lot of the problems. Okay. And I'm going to finish with talking about energy in a wave. Now, we're going to see how does the energy in a wave vary with the distance. Okay. Now, if it's a two-dimensional wave, meaning like if you drop a pebble in water in a lake, right? That's 2D. So let me see. The energy per unit circumference, length is, and per unit time crossing a line perpendicular, blah blah blah, is proportional to 1 over r. So if it's 2D, as you go further out, your energy, okay, decreases just linearly with r. Okay, but it decreases, it doesn't increase. And it kind of makes sense because when you first start, when you drop that pebble inside the water, you have a small circumference here, but as the wave travels further and further out, all that energy that you started with here has to spread itself over a larger area. Okay? If it's a 3D wave, like sound, when you generating sound, sound travels in all directions. So it's a bunch of like spheres, okay, traveling away from the source. Okay, so it's not like circumference, but it's more like a sphere. It's not an area, but it's a volume. In that case, the energy changes as 1 over r squared. Okay, we're not going to do the proof to this, but that's how it works, right? But most of the time when we're going to be dealing with sound, so we have to know that the sound intensity is going to change as 1 over r squared. And that should do it. I think in the next video I'll do some of the problems. We'll do a lab and we should be done with this in like 2 days or so. Okay. All right. Thank you. All right. I'm out. Peace.